You know that feeling, right? You're on a web page, you click, and nothing. It's completely frozen. It's got to be one of the most frustrating things ever. Well, in this explainer, we're going to dive deep into why that happens, specifically with JavaScript, and we'll uncover some seriously powerful tools to build apps that are just lightning fast. Let's get into it.
Oh yeah, we've all been there. You're trying to click a button, scroll down a page, anything, and it just stops. The entire UI is completely unresponsive, held hostage by that dreaded spinning wheel. You might think, well, that's just how the internet is sometimes, but it's not. It's actually a symptom of a very specific and fixable technical problem.
So why does your UI die like that? What's actually going on under the hood? Well, the answer gets right to the heart of how JavaScript itself works inside your browser.
Okay, so to get to the bottom of this freezing problem, you have to picture a massive traffic jam. And the cause of that traffic jam? It's something fundamental to JavaScript, its single-threaded nature. This is the bottleneck.
All right, so what on earth does single-threaded even mean? Put simply, it means JavaScript can only do one thing at a time. It has this one main thread, and that single thread is responsible for everything. We're talking clicks, animations, running your code. All of it has to line up in a single strict queue and be processed one by one. Here's the best way to visualize this. Think of that main thread as a single-lane highway. Every single task, a click, a scroll, a bit of code, is like a car, and they all have to drive down this one lane. As long as traffic is light, hey, no problem, everything flows smoothly.
But what happens when a really heavy task shows up, like, say, processing a huge image or running a massive calculation? Well, that's like a gigantic, slow-moving truck pulling onto our single-lane highway, and it just grinds everything to a halt. It blocks all the cars behind it. So your clicks? They can't get through. Scrolling? Stuck. Animations? Frozen solid. Your entire UI is now caught in this massive traffic jam. That's your frozen page.
Okay, so if the problem is a single-lane highway, what's the solution? Well, you build more lanes. And in the world of JavaScript, these extra lanes have a name: web workers.
So, what's a web worker? It's basically a way to run a script on a completely separate background thread. And let me tell you, this is a huge deal. It means we can take those slow, heavy-duty tasks, our giant trucks, and get them completely off the main highway. We move them onto their own special express lane, which lets all the normal UI traffic, the clicks and scrolls, flow freely again.
Now, it's really important to understand the difference here. The main thread, that's for the UI. It has to stay fast and responsive. The worker thread, on the other hand, just chugs away in the background, completely isolated. And that isolation is actually a safety feature. A worker can't directly mess with the web page. It can't access the DOM. And that prevents all sorts of messy problems you'd otherwise run into.
Okay, so if they're totally isolated, how do they talk to each other? Well, they pass messages back and forth using a function called post-message. The main thread can send some work to the worker, and the worker can send the result back when it's done. But, and this is a big but, the data is copied, not shared. For a little bit of data, that's totally fine. But what if you're sending a huge file? That copying process itself can be slow and create a whole new performance bottleneck.
So web workers are great. They solve the UI freezing problem. But that data copying thing can still be a drag. If we want to build truly high-performance web apps, we need a way to get rid of that copying step entirely. We need to unlock true shared memory.
I mean, think about it. Copying huge chunks of data between threads is just inefficient. Imagine you've got a gigabyte of video data you need a worker to process. Just the time it takes to copy that gigabyte would be a killer, not to mention the extra memory it eats up. There's got to be a better way, right?
And of course, there is. It's an amazing thing called a shared array buffer. Instead of making a copy, this lets both the main thread and the worker thread look at and change the exact same block of memory. It's a zero-copy operation, which means it's incredibly fast. And the difference here is night and day. With the old post-message way, you get two separate, safe copies of the data, but it can be slow. With shared array buffer, both threads are operating on the very same piece of memory. It's blazing fast, but it also means, well, you have to be a lot more careful.
I mean, what happens if two threads try to change the same piece of memory at the exact same time? That's what's known as a race condition, and it can cause total chaos, corrupted data, unpredictable results. It's bad. So with the great power of shared memory comes the great responsibility of managing it. And to help us do that, we have another tool, atomics.
Atomics is basically a set of special operations that are guaranteed to be, well, atomic. That means an operation, like adding a number or reading a value, happens all at once, without being interrupted. No other thread can jump in halfway through. You can think of them as the traffic cops for your shared memory. They direct the flow, prevent collisions, and make sure everything stays in order.
Okay, so giving JavaScript direct access to memory is incredibly powerful. But, as you can probably guess, it also introduces some potential security risks. Because of that, browsers don't just let you use these features willy-nilly. You have to opt into a special, extra secure mode first.
So, a few years back, some really serious security bugs like Spectre were discovered. They basically showed that it was possible for a malicious website to peek into the memory of other websites you had open. That's a huge problem. So browsers actually disabled shared array buffer for a while. When they brought it back, they did so with a brand new, very strict security requirement called cross-origin isolation.
And to turn on the secure mode, you have to configure your server to send two specific HTTP headers with your web page. They're a bit of a mouthful: Cross-Origin Opener Policy, or COOP, and Cross-Origin Embedder Policy, or COEP. What these do together is basically tell the browser, hey, lock this page down. Don't let other random websites mess with it in ways that might be insecure.
So, how do you actually implement this? Well, you don't want to just flip the switch and break your whole site. There's a process. First, you use report-only versions of the headers. This lets you see what would break, like maybe a third-party script or an ad, without actually breaking it. Step 2, you fix those issues, maybe by working with those third parties. And then finally, once you've got the green light, you switch to the real headers to lock everything down and unlock all these amazing concurrency features.
Whew, okay, we have covered a lot of ground here. We've gone from single-lane highways and traffic jams all the way to shared memory and security headers, so let's kind of zoom out and bring it all together. Why is knowing all this stuff so incredibly important for any web developer today?
All right, here are the key things you need to remember. First, the main thread is sacred, protected at all costs. Second, use web workers to offload anything heavy and keep your UI smooth. Third, when you need maximum performance, shared array buffer is your friend for zero-copy data sharing. Fourth, if you use shared memory, you must use atomics to keep your data safe. And finally, none of this advanced stuff works unless you enable cross-origin isolation with those special headers. Got it?
And if you're wondering, does this really matter for my career? The answer is 1000% yes. Take a look at what the big tech companies are looking for in their interviews. Right there, next to the classic data structures and algorithms, you see it: async programming and language mastery. Knowing how to handle concurrency is not some niche, nice-to-have skill anymore. It is a core competency. It's what separates the good developers from the truly great ones.
So I want to leave you with this. The next time you're working on an app and it feels slow or janky, ask yourself this question: is there a hidden traffic jam on my main thread? Is that single-lane highway the real bottleneck here? Because after this, you don't just know what the problem might be, you know exactly how to fix it.